Welcome to the webinar, everyone. And today I'm going to talk about training neural networks on a single CPU. So if you are interested in using multiple GPUs to train your neural networks, please refer to my previous seminar. There is a recording on our YouTube channel. You can find it there. So let's get started. So deep learning is no doubt the very popular topic nowadays. It has been used to solve many challenging AI problems, such as image recognition, speech recognition, and many, many more. And the GPU plays an important role in deep learning. So here is a benchmark that I did using a small convolutional neural network, which I will introduce shortly. So the benchmark actually compares the performance of GPU versus CPUs, to see which one is the best. And in the benchmark test, I fixed the training task by using the same training parameters for all different hardware settings. So the graph here shows the timing of using different number of CPUs. You may wonder why the timing, the training time by 2 CPU is not half of that of by 1 CPU. This is because the training process is not 100% parallelizable. That's one reason. Secondly, there is always some overhead in parallelization. So the same explanation applied to others, like using 4 CPU versus using 2 CPUs. You won't see the timing is being cut by half. That's not possible. And you can also see that there isn't much improvement from using 16 CPUs to 32 CPUs. This is because it pretty much breaks even between the benefit and the overhead of using multiple CPUs. So you can see the timing here. Then how long it takes for a single GPU? Only 150 seconds using Pascal 100 GPU. So roughly speaking, 1 Pascal GPU is 15 times faster than 16 CPU cores. So this is just rough speaking, because if you use a different neural network, then probably you got a little bit different benchmark results. But the fundamental conclusion is the same. GPU can greatly accelerate neural network training. Now, we know the benefit of using GPU in deep learning. So now we are going to explore further the frequent asked question, such as how to check the availability of a GPU. If there is a GPU available, how to make sure my code is running on that GPU? Or if it failed, is that because my network is too big to be trained on that single GPU? So on and so forth. We are going to address those questions in the rest of the talk. All right. So I'm gonna use a small convolutional neural network, for handwritten digit recognition as an example to illustrate how to visualize and understand the architecture of the neural network. And then we try our best to estimate the major factors that affect the memory usage. I'm going to also show you how to check the GPU memory usage at runtime. And finally, I will give some suggestions if your neural network is really too big to fit in into a single GPU. So what can we do in that case? All right. So before we move on, so let's take a quick look at the GPU resources we provide at Compute Canada. Most of our clusters have GPU nodes. You can see that here. For example, Graham has 3 types of GPU nodes, Pascal 100, Volta 100, and T4. So today, I'm gonna use mainly the Pascal 100 to do the demonstration. So here is the whole process of a single training iteration. So it starts with feeding a batch of images or a batch of samples to a network, which will, I see there's some chat. Is that because, who's that? Sorry, go back. So the first layer will take the the batch of images as the input X, and produces output Y, and the parameters of the layer W determine the mapping from X to Y. So the calculation goes through the network from layer to layer until it gets the final output of the neural network. At this point, it completes a so-called feed-forward pass, and we need to compare the output from the network with the ground truth or desired output to see how different they are. So we use some kind of predefined loss function and to describe the, to measure the difference. And then we need to go through a backpropagation process. In the process, we need to modify the weights or the parameters so that the network will produce output that close to the desired values. So how to do this? Basically most of the method is so-called gradient descent. So basically, you need to calculate the derivatives of the loss function with regards to the trainable, to each trainable parameter. So this looks like a daunting task at the first glance, but fortunately, we can decompose the calculation based on the so-called chain rule in the calculus. So basically, you can do it layer by layer, and so in the backward direction. So once we calculate the derivative of each trainable parameter, we use the gradient descent to update the parameter. You know, how much we're going to change it is determined by the learning rate we defined. So that's the the principle of how the training, neural network training works. Okay. Next, what's the typical way to estimate GPU memory usage before running? The basic method is called a shape inference. It actually estimated the 4 components. That is memory for the trainable parameters, memory for the outputs of intermediate layers, and finally, in the backward propagation path, we need to keep the derivatives of the outputs from the layers and the derivatives of the parameters. But some people argue that we do not need to keep all of them because those derivatives are calculated in a layer by layer manner in the backward direction. So basically, once derivative is calculated, we use it, update the weight, and we throw them away. So we don't need to keep all of them all together. But that's just lastly, we need some memory for some temporary variables, some workspace, and also remember that GPU memory, you need allocated, deallocated the same way as we treat the CPU memory. And there's always a fragmentation problem. So you want to keep a fragment as small as possible. So there's a lot of, so basically shape inference is not so accurate. And we need some other way to figure out a way to estimate it. Another way is to to compare, to estimate by compare with some benchmark neural network models. So we already have some models like those famous one. So here's a graph shows the memory usage of those models. For example, AlexNet, which contains 5 convolutional layers and 2 dense layers. And if we train it with batch size 128, it requires 1.1 gigabytes. It's the smallest one. And for VGG 16 extended model, it contains 16 convolutional layers and 3 dense layers. So if we train it with 256 samples as a batch, then it requires 28 gigabytes. So I need to point out that there is another factor that affects the memory requirement that I didn't include in this slide. That is the size of the sample. So for those models, because they are all used for image recognition applications, the samples actually, one sample is just 1 image. So the size of or the dimension of the image matters. And I remember some of the model, I'm not sure it's AlexNet or VGG, they use image size is 224 by 224. And probably it's a color image. If that's true, that means there's 3 channels. So 224 by 220 by 3. So it's quite large compared to what I'm going to introduce next. All right, so now I think I'm gonna show you very simple neural network, convolutional neural network for handwritten digit recognition. The reason I choose it because it's relatively small, and the code for constructing such a network is very short, easy to understand, and also it contains most of the commonly used layers like convolution, dense layer, pooling, dropout. So let's take a quick look at this one. So I'm gonna log on Gram. Okay. So I'm gonna switch to the directory. I think I put it into yes, here. So just quickly show you, because I already set up a Python virtual environment. So what I'm going to show you is you see I installed TensorFlow GPU version. I installed the PyDot, which is used for plotting by Keras. Lastly, I installed another package called NVIDIA ML. That is for, to do the NVIDIA SMI in the Python environment. Okay. Oh, sorry. So basically, let me. Okay. Probably let me check job. Today I'm gonna use a reserved. I'm gonna run it. Let's say I use 1 hour. Sorry, 1 hour 50 minutes. I think that's it. Okay, so I'm on it. I'm on GPU node 837. So I'm gonna open another one. So what I'm gonna do is I'm gonna SSH to that node. The reason is I will show it later on. So basically here on this window, I'm gonna, can I switch the window order? Yeah, I think I can do. So for the first window, I'm going to use it to do the main work. So first I'm going to activate my virtual environment. All right, so now you can see, if you want to see, you can see I have TensorFlow 2.2 installed there. It's pay attention, it's a GPU version. And if you do the same thing now, I think right now we have 2.3 available now on Computer Canada clusters. But I think the performance may be the same. All right, so I activate my virtual environment. So now I'm going to go to my my source code. First, before running, let's take a quick look. The code is not very long. I'm going to go through it. So the first block is the input block. So I input a lot of modules that I need later on. And you can see that because TensorFlow has its own implementation of a Keras interface, so I use the TensorFlow's Keras interface instead of use it alone, so it's more convenient. And next, I define some global parameters that we'll use later on, like learning rate, batch size, and the convolutional kernel size. I call it filter size, and so on and so forth. So let's begin the next part. So the step one basically is I'm loading the data. So basically I'm loading the data using very convenient module from Keras. So I just want to mention that if you don't understand the code right now, if you need to study it later on, I will provide a link for you to download the code so you can try by yourself, okay? So after the loading, you got the training data. The first part feature, the second part is the label, the test set feature and the label. And when I say feature, actually it's just 28 by 28 images, grayscale images. And the label is just a label indicating it is a digital 0 or 1 or 2 or 9, something like that, okay? So then I print the shape. You can get a quick understanding of the data. After that, you extract the row and column, because the shape 0 is the number of the samples in the training set, okay? Because we define the number of iterations as the number of steps, and Keras needs another measure called epochs. So I converted it into epochs from the number of iterations. It's just a different way to specify the same thing, okay? And after that, we need to, based on the format requirement, if either is a channel first or channel last, we will reform the input shape. Why we need to do that? Because this looks strange at the first glance, because here, as I mentioned, it's a grayscale image, it's not colored. So the channel is just 1, not a 3. Why we need add a singular dimension? Because if you are familiar with MATLAB, MATLAB has a function called squeeze to remove a singular dimension. But why? But here the point is, TensorFlow require the order. Even though it's a singular dimension, we need to make to have it. Otherwise, it's just some grammar issues. So we need to make that happen. So here, if it's a channel first, you see channel, row, and column. Or otherwise, it's a row, column, then channel, just one channel, okay? Something like that. So just reformatting. Another reformatting is this part, because the input data is integer from ranging from 0 to 255. I just do the conversion to map it to a float from 0 to 1. So just some. So at this point, I finished the data reformatting. So I have the data ready. Oh, now the last step is I need to convert the label into so-called one-hot vector. So you can check, you can Google what is one-hot vector, which is a vector length of 10. Only one of them is 1. All the rest are zeros. Okay. Step 3, we create a sequential model, and by adding each layer by layer. So first we create the first layer is convolutional layer, and we need to specify the number of kernels, which is 32. If you go up, you see 32. The second one is of 64. Okay, let's go back. 32, and the kernel size is 5 by 5. This is 5 by 5. And I specify activation is ReLU, and I need to specify input shape. Why I need to do that? Because this is the first layer that I have to specify. Otherwise, for the rest of the layer, don't have to specify, because TensorFlow can figure out the dimensionality or the shape of the output from the previous layer. Okay, so after that, I X up a max pooling, reduce the image size by half, and then another convolution, and followed by another max pooling. After that, the output from the pooling is a three-dimensional image. That is width times height times channel. And we need to flatten it to make it become one-dimensional so that we can concatenate that into the next layer, so-called a dense layer. Dense layer is also called a fully connected layer. So we do that fully connected, then we add a dropout to, just it's a kind of regularization is a way to overcome overfitting. And then another dense layer to get the so-called output. So at this point, we have 10 output. And because we use the softmax as activation, the output looks like a probability. So the sum of the 10 output are, the sum is 1. And each of them, ranges from 0 to 1. So it's just like a probability. So it just tells us what it's likely to be 0, to be 1, to be 2. So normally we choose the biggest one as the output. Okay. So lastly, we train our model with only one one function call called feed. So we feed in our training data, and we tell it how large is the batch size, how long we're gonna train it. That's it. It's all done with one function call. Lastly, we check the model's accuracy. But here, actually, I don't care, because here we don't care about how accurate we can train our model. We basically focus on, how long it takes, whether or not the model can fit into GPU memory. Okay, so let's give it a run so that we can see. So because now I'm already on the a GPU node in the interactive session, I just type Python, and I give the Python code, hit return key, and it's gonna run. But before run on this, because this I already log on, that node, NVIDIA SMI. So I'm gonna watch the performance. Oh, sorry, I did something wrong. Oh, sorry. Instas environment. Okay, so you can see some low like 50. The GPU is 53% of BZ, not of sometimes 51, 52. And so this is the memory usage. So at least you see something that is not. So I'm going to terminate because I don't want it completed. Let's roll back. You see at least it looks good. It's keep in the first after the first epoch, we already get like 85% of accuracy, then 95, and then close to 99, 90. Sorry. So that's our first run. So it looks good. Next, we are going to show you how to estimate the architecture. So let's move on to another one. So let's look at another one. So basically, we grow our code from the previous version by adding something. So here I add this one. Add a plot model, which is a module of Keras utility from that. Then the same code I don't need to repeat Then I add something. Okay, after I built the neural network here, I add 2 lines of code. Okay, 2 lines of code. One is called a print model summary. So this is the model that I created. Sorry, I did. This is the model that I created previously, this one. And then I just print summary. It will give me the result. Secondly, if I want to get a graph, I use a plot model, and I will give a PNG file, so I can save the plot into a PNG file. And I want to show the shape, I want to show the layer name, and so on and so forth. So let's give it a try. Python, sorry. Copy paste, faster. So here I'm going to watch again. So on here you can see the load is 0. Oh, now it's running. So go back here. We should see something here. Yeah. So I'm going to stop here because I want to see something beforehand. So basically, it print out this information. This is what we get here. Okay, this is what we get from the print summary. Okay, and it shows the first layer is convolutional layer, and you see that the shape of the output is 24 by 24. You wonder why it's like that. So let me explain first. As I mentioned earlier, the input is a 28 by 28 image, okay? And because we use a filter size of 5 by 5, so when you move a 5 by 5 within 28 by 28, if you do not use padding along the boundary, you will get a 24 by 24, okay? And also because I use 32 kernels, I got the result of 32 channels. You may also notice the none here, because at this point, right after we construct the neural network, before we train the network, we don't know how many samples in a batch or the batch size. So it's none. So because it doesn't matter. So we give a none. Okay. The parameter for this one is 832. I will explain how many why the parameter is this one, and then is this one, and finally the total number of parameters is like a little bit over 1 million. Why is that? Okay, but certainly you need to understand the shape of the output from each layer, so it will help us to. So this is the result from it's so easy by just printing out, and we should also see the PNG file. Okay, see here, we got that one at 1235. So let me. I'm gonna display that one. Project. Okay, so let's give it to see how. Let's display the PNG file. Takes a bit long. Okay, here. Sometimes it takes a bit. So this is basically the same information, but in a more graphical format. So you can see the first layer is the convolution layer. It's also, instead of showing the output only, it includes both the input and output. I think that's nice. Okay, so basically the same information. So here, I just, show you how just with the 2 lines of code added to the original one, we can, get a good understanding of the architecture. Okay. So now let's go back to see how we make up these numbers. Like I said, the first one, we have 32 kernels, convolutional kernels, and the size of each one is 5 by 5. So, and also for each kernel, we need, there is a BIOS associated with each kernel. So the total number of parameters is 5 times 5 plus 1, and then multiply with 32. So the same way we calculate the next convolutional layer, the parameter for the next layer is in the same way for the dense layer, because after the previous layer, the output is actually 1024 by 1024, and we multiply the number of 1024, which is defined the number of neurons in the dense layer. And then also there always are BIOS associated with each neuron. So there's an actual one. So we plus 1, then times 124. The last dense layer is that we have 10 neurons on the last layer, but the input connection is 1024. Like I mentioned earlier, they always a plus 1 because there's a BIOS which associated with each neuron. So that way we got the number. If we sum of them together, we got the number of 1111946. Yes, you can do the calculation yourself. All right. And then the next step, we try to estimate the GPU memory. Like I mentioned earlier, shape inference alone is not accurate, but what can we do? Let's do our best. So here is my way to calculate it. So this is the total number of parameters, and each of them is in float. So one float contains 4 bytes. Why we need 2? Because like I mentioned earlier, we need one for the parameter themselves. The others is for the derivative of them in the backpropagation path. But some people argue it's not necessary, but I included it here. And the next one is for the intermediate output. So I basically do the same calculation, and this is for a single image. Remember that for single image. And finally, I got a single image and need this amount of memory. And altogether, I can sum up previous one altogether. So it's like 8 megabytes plus the batch size times 0.229. So that will give you an estimation. So in my calculation, I do not include the miscellaneous memory for like temporary variables, workspace, so on and so forth. So it's not going to be accurate. So here is the result. The blue bar shows the runtime memory that I measured with NVIDIA SMI, and the red bar represents the estimate ones. You'll see a huge difference. Like I said, because one reason I didn't include the first part. And secondly, I think the runtime memory that I measured shouldn't take as a golden standard, because you can see that once I increase the batch size from 8,000 to 16,000, we do not observe a big difference, almost no difference. It's so it's all depends on the GPU memory allocation, deallocation strategy. I wonder, probably it's possible that it used more flexible strategies, such as if it finds the available memory is low, maybe it used the memory more conservatively. I don't know, but but I think basically. Estimation of GPU memory is not very practical, okay? So now let's move on to the next question, how to train our model on a GPU. So to make sure that first you need to make sure you install the GPU version, not the CPU version. Secondly, you need to use the Keras to specify, GPU resource in your Slurm command. Okay. So let's move on to the next one. So let's look at does my training running on a GPU. So here there's some way. So first thing is you can find something like a physical GPU or something print out in the printout. Let's take a look again. You can see that move on here. So you can see created. Well, I just highlight here. You see, like a device name is Tesla P100, so on and so forth, 12 gigabyte memory. So we see that. So that means the system detects the availability of this GPU and also using it. And if you are not still worried about it, you can, check the availability of GPU in your code, and also log the placement of operation. So you can see each operation is executed on which device. It's a CPU or GPU. We can do that. So let's do that. Let's take a look of the second one. Let's see. First of all, you need to input TensorFlow as a TF. So you basically use this function call to get the physical device, GPU device. You can probably, if there's multiple GPU available, you can get a list of them, and you can print how many of them are available and the name of each one, so on and so forth. After that, this one is very important if you really want to see verbose printouts that shows every operation on which device it is executed on. So you need to switch it on, but to make that one, to turn it on, it's very verbose. So let's run it, sorry, Python. Let's run it. So let's take a look on this side. So you can see here, 0, 0, now it's getting something there. So it starts running. So let's go back. So you can see it's so, I turn it off. So I stopped the execution. You can see previous one, like the Adam, solver running on GPU, and if you roll back and to see some other task, let me see, there's some other calculation like a gradient weight lost and so on and so forth, softmax, you can see which one they are executed, they all specify GPU. So now you are confirmed that your code are indeed is indeed running on GPU. So that's one way. And another way is you monitor the GPU memory usage or the activity. Like I mentioned earlier, when it starts, you see this number instead of 0, you get some number. Also, you see the memory will change from 0 to some number. So that is another way to assure that your code is running on on GPU, okay? And if you want to try, for example, if you really want to try, if there's no GPU, what will happen? So I probably can do a quick test. So here, I'm on a login node. Let me source activation. So I'm gonna run my code on my on login node. Please do not do this on login node. I'm only run it and then stop it right away. So hopefully that doesn't interrupt anyone. I just want to give you a quick look what it will look. Okay, so what it does is no CUDA capable device is detected, failed. Okay, that's it. So that's something you will see. And let's move on to next one. Monitor at the runtime. So we have used watch. So we watch the command every second to get update every second, so we can monitor the usage. And another way we can use the NVIDIA package, Python package to monitor the usage in our code. Okay. Another way is you sub process is the same way as you run the command manually. So let's do it. Oh, sorry, we shouldn't do this. So let's move on to the GPU node again. So let's do run it. First, let's run it again. Let's watch this one. So you'll find that at the very beginning, even when the load is very low, like 1%, 2%, it soon fill up this one. It's almost use all the GPU memory. So I doubted that my small neural network will use such so much memory. So it's obviously wrong. Why is that? So the reason is, so I'm gonna stop the execution. So the reason is like this. By default, TensorFlow will allocate all the available GPU memory so it can use it more efficiently. And so even though we just need a small fraction of it, so to make it use as needed, we need to specify this one to make it, to turn it into memory growth mode. So how to do that? Let's take a look of our code. This 3, right? Okay. 2, 3. Let me check this one or just is that A3? Oh, here, yeah. So basically here you can see first I get a list of GPUs. In this case, I only get one, and I set it to be, memory growth mode to be true. So then I can, monitor the, so this is the version, that's the only thing that I changed. So I'm gonna run it. So basically this is the same thing, just I turn the, into memory growth mode. So to see if we can get the correct memory usage. So let's monitor it. Just give it, just wait. So you see now, it's much smaller. You see on 800 meg, less than 1 gig. So it makes sense. So because it's just such a small neural network, shouldn't take that big memory. So I stop it. And lastly, what I'm gonna to show you is how to monitor the usage in the code, okay? So it shouldn't be very hard at all. So I just switch back to the last one. Let me, okay, it's here. Basically, it's here. Although the code are a bit longer, basically what I did is I first, previously I think I initiate a little bit somewhere. Let me move up. There must be some initialization somewhere. I quickly, okay, here. So first I initiated the library, the so-called NVIDIA SMI library, and get a handle. Once I have that handle, let's move down to here. What I'm gonna do is from that handle, from that handle, I will get to quote information. That information contains a lot of things like the total memory, the amount of free memory, and the used memory, and then I shut it down. But because we get the GPU memory usage, only at that moment this function get called. But at that moment, if we didn't start the training, we won't get an accurate measurement. So basically, I add an extra, feed command. Basically, I just feed with one epoch so that I can get accurate, measurement. And then later on, I can keep doing the epoch, the longer one. So let's give it a look to see what we have. All right. So we can still switch to here to monitor. So now it starts running. So I'll give it a look. So after that, so okay. So here, I just stop it. So here you can see this is our printout. You can see the memory, the usage. It's exactly what we see, the used memory is just 800 megabytes, okay? So I have probably almost, there's only one thing that left on my agenda. So this summary, how to use it. Okay, the last thing is if we want, we can blow it up by make our network larger. The reason is probably somebody may wonder if what it looks like if we, if the network is too big. I think I won't do it here because I just want to let you do it. You can try it by yourself. To make your network larger, you can either make it deeper by adding more layers, but here, instead of making it deeper, I make it fatter by, just simply increase the size of, the layer by making those changes. Then you will see something like this. I leave it for you to try. So once you see some information like this, you know you are running out of GPU memory. So what can we do in this case? If your neural network is really big and if you need keep certain batch size to get a stable training. So first of all, try best to reduce your batch size. Secondly, try to reduce the scale, the size of your neural network. If that hurts your accuracy, you may consider do some low-level customization, and this requires you have the knowledge of the low-level API of TensorFlow or Torch, if whatever library you are using. And lastly, I find this interesting library. It's from IBM. Actually, it does exactly the same thing that I want to do, but instead, you don't need any in-depth knowledge. You just use it. So if you download this Python package, it's supposed to do what you are supposed to do, to overcome the out of memory problem. So I haven't tried it. If you like, you can give it a try. And let me see what we have left in our agenda. Lastly, it's just a joke. So please do not wait for the next generation CPU with large memory, okay? Try to do your best okay? So here are the links to my slides and the code. I will post it in the YouTube channel once the recording is ready. So thank you so much for your attention, and I'm thinking I'm a little bit run out of time. So now let's answer the question.